Today, we will continue with selected algorithms, and concretely, something that I've also added this year is random number generation. All of us use random numbers all the time. When you, for example, initialize values and you want to have some randomness in an experiment, whatever. So random numbers are quite important in computing. And if you use Python, you just use the random module and you can generate random numbers. But probably you're wondering, where are those random numbers coming from? Because you can use a library, but what are they doing in the background? And it turns out there are some approaches that are relatively easy to describe, and they generate random numbers for you. And we'll be discussing one of the early or a relatively good approach, which is yet simple. If you use a professional random number library, probably they do something more advanced though, but we can at least discuss one way how we can generate random numbers in like half an hour. So generating random numbers is tricky. If you want to have real random numbers, you actually need hardware random numbers or hardware random number generators. So you need some physical device that interacts with our physical environment, and it sort of generates numbers that are not really possible to model, and then you would sort of have your random numbers. But such devices are expensive, and that's why on our computers today, what we use is pseudo random number generators. They are mathematical models, and they generate numbers that are not random, but they appear to be random. They are predetermined. There's not really randomness in it, yet they do quite some tricks. So the numbers we get appear to be random, and they're cheap to compute, and you don't need any extra hardware that interacts with our environment. We'll discuss one approach now, and first of all, we have to look at a recurrence relation, which is called the logistic map. This, first of all, doesn't really look like it's related to random numbers, but we first need to define this logistic map, and then we'll actually see how it behaves. And then we will later see that this can actually be used as a pseudo random number generator. So a logistic map is a recurrence relation of degree 2, and it's something that inhibits or exhibits complex chaotic behavior from a very simple nonlinear dynamic equation. And this is something that became popular in the 70s by a paper, but it's probably existed for a longer time. The logistic map looks something like this. It's a recurrence relation. So our new x, so x at time n+1, is our old x times 1 minus x, and we multiply all of that with r. Our xn is a number between 0 and 1, and our r also has some impact, and we will discuss the value of r very soon. And depending on how you set r, this logistic map exhibits chaotic behavior or not. I will briefly write it down on the iPad, so but I'm not switching to the iPad because we'll need the iPad only later. But I'll write it down as a note now because we'll work with it later. There is a lot of interpretation of what this logistic map does. It's been used, for example, to model behavior of populations, of how much a population grows or shrinks, because this has a clear link to the logistic function. So you need some reproduction and starvation, but this is more like the theory behind it, which doesn't matter to us because we'll be using this to generate random numbers. What is important is our xn that we saw before remains bounded on 0 to 1, where 0 and 1 are included in this interval. So xn is between 0 and 1. And our r, which is a parameter that will influence if the model behaves in a chaotic way or not, r is between 0 and 4. And depending on the exact value of r, we will see chaotic behavior or not. We can try this out. And for this, I'll switch back to my iPad. So we can start and say r is 2. And we can say we need to start with some value for our x. So we say x0 is 0.5. And now we can try to calculate x1. So x1 is 2 times, or we'll start easy. It's r times x0 minus, or times 1 minus x0. So this would be 2 times 0.5, because r is 2 and x0 is 0.5, 1 minus 0.5. So this is 1, and this is 0.5. So eventually our x1 is again 0.5. We can try to calculate x2 now, which is r times x1 times 1 minus x1. And you will see that this is eventually still 2 times 0.5, 1 minus 0.5. And again, this is 0.5. So for R2 and x0 is 0.5, eventually this doesn't change anything. X1, X2, X3, and so forth, they are all 0.5. So it appears that when R is 2, the x0 doesn't really change when it starts with 0.5. We can now go back to the slides and try this with a few other values and see how all of that behaves. We can say, well, now our x0 is 0.2, and our r will just stay at 2, and you can try out these calculations at home. So r is 2, but our x0 is this time not 0.5, but 0.2. Then our x1 is 0.32, x2 is 0.43, and so forth. And we see that all of this will also somehow converge to 0.5. You can also try to visualize this. Very importantly, r is 2 and x0 is 0.2. And eventually, after a few steps, x seems to converge to 0.5. This figure is from a very interesting book that is called Complexity, a Guided Tour. This is a book I read last year during the summer break, and discusses complexity from many different perspectives, not just computational, but also from physics and many other disciplines. And the book introduced this logistic map and using it for random number generation. It was just one of many things discussed in the book. But I found this interesting, and that's why I added this to the course this year, because it's a fairly simple way of how we can soon generate random numbers. So if you're interested in complexity, feel free to read that book. I read it last year during the summer and enjoyed it a lot. Now we can try to make a few changes. And this time we can say, well, x0 is 0.99. And we will see after a few steps again, this will converge very quickly to 0.5. So no matter what we put in x, that is between 0 to 1, for r equals 2, this always seems to converge to 0.5. And this is definitely not a good random number generator, because very soon we will only generate 0.5. So probably not a good way of generating random numbers. But we can now try to vary our r. And if you change r to 3.1, and we start with an x0 that is 0.2, we will see that the value of x starts to oscillate somewhere between 0.79 and 0.55 maybe. Yet these upper and lower bounds are always the same, so we just have an oscillation, but still nothing that really appears to be random for our r that is 3.1. Now we have a change because we changed r, and now at least we have oscillating behavior and not this convergence anymore. And we can try to change r again. Let's change r to 3.49. And now we have, again, some oscillation, yet there is still some pattern we can see, and that somehow this keeps repeating. Probably still not too great as a random number generator. And now we can change r again, and we change our r to actually 4, and r is 4. And our x0 is 0.2, which starts here. And then we see this really seems to inhabit sort of chaotic behavior. We don't really anymore notice a pattern in here of how the values of x keep repeating. And what is also interesting, if we put in an x that is slightly different, so another x0, which is 0.2, and then a lot of zeros and a 1. We put this in our logistic map as well. And initially, we have sort of the same behavior, but later on, we see that these two actually keep diverging. So we have our filled line, which was the x0 at 0.2, but we also have this dashed line, which was for this slightly larger x0. And we see that finally, this keeps changing quite a lot in here. So, and that's actually what chaotic behavior means. We put in a slightly different input, and after a while, the outputs are completely different. So this logistic map can in fact be used as a random number generator, at least as a simple one. Very importantly, if you use like the Python random module, you'll be seeing something far more complex. Not just that simple, but this logistic map can also be implemented, in fact, very easily. And we can try this out now. So I'll show you how to code it. And I'll do the screen share in a second. So you should be seeing the screen share now. And we can call this generate random numbers. We want n many random numbers, and we also want a seed. A seed is some initial value you can put into a random number, and when you put the same initial value, then you would get the same outputs. So this is something that you also often see in random number libraries. But instead of the seed, you could also just put in like the system time or something, and then each time, instead of your seed, you just put in the system time or some value derived from your system time, and then really have something that even behaves more randomly. Our R is 4, and we want to generate results. So we not just want to generate one random number, but multiple. Our x0 will be just the seed value, so like 0.2 or 0.3, whatever. And we can go through now our range and generate n many random numbers. So x will be r times x times 1 minus x. Oops. I probably have some strange typo in here. I don't know if you see, the in is missing, thanks. Because it should not have terminated here. Thank you. I didn't see the in. And then we append this to the results and return the results. So we can try this out, generate random numbers. I want 10 random numbers with our seed value 0.2, and I get something like this. I can also put in a different seed value, and I get something like this. So we see I put in a different seed value, and I get something that appears to be quite random. I don't see any intuitive pattern in here for this number of n. And again, the seed, when you put in the same seed, yes, you get the same sequence. So this allows you to reproduce an experiment. But rather than a fixed seed value, you could calculate some value from your system time or something, say the number of milliseconds in your current system time or something you would put in here, or something more complex. And then each time you call generate random numbers. Rather than your fixed seed, you would put in, instead of that, just that value derived from your system time, whatever. And then each time you call it, you get a different sequence. So you see, calculating random numbers is not too complex. There is a question here: how would one put a DT object in there? Maybe you can tell us what DT stands, like data, whatever. Datetime. Okay, thanks. You would just access the system time, and maybe this is just one suggestion of what you could do. So you wouldn't put the datetime directly in here, but you would calculate something from the datetime, maybe the number of milliseconds or something. And it's something you can easily try out at home by getting the date, time, and then taking out the seconds or milliseconds, whatever, and just put in some seed value that is between 0 and 1. Don't put in directly 0 or directly 1, because this will just ruin this one here. So you would definitely have to check that you're not putting exactly 0 or 1 in, but something that is a little bit greater than 0 and a little bit less than 1, because otherwise you will have a 0 in this multiplication. So you would need some epsilon on top or reduced, just to avoid that from happening. But should be fairly easy if you access the date time. So now you know how to generate random numbers. You can obviously do this for more than 10. You can generate 50 random numbers. And this looks relatively chaotic, and you will not sort of have a pattern that you're noticing. This works because our R is 4. If our R is less than 4, this will not work. And in the book, you can also find a so-called bifurcation diagram, probably a term you never heard before. And what this bifurcation here shows is sort of the chaotic behavior if you have a very small R, like 2 before, we saw it converged. But when you make your R larger and larger, you have more spread out, and you will have real chaotic behavior at R is 4. And that's exactly what we've just implemented. So you see, just implementing your own random number generator is not that difficult. You can just do this like in about 10 lines of code, which is definitely fairly easy. In practice, probably you would be using a more complex random number generator, but now at least you know how to build your own